Okay, here we are again, last lesson in exponential and logarithmic functions, and we're going to talk about logarithmic scales and applications. What a logarithmic scale is it's a scale that compares values in some way using powers of 10. So the three that we're going to look at are earthquakes, so the Richter scale. We're going to look at loudness of sound, so decibels, and then we're going to look at the pH scale. And this is just a little history of the Richter scale. It's named after an American seismologist named Charles Richter, who lived from 1900 to 1985, and it's used to measure the magnitude of an earthquake. The magnitude of an earthquake is a measure of the amount of energy that is released. And we don't need to know how that is actually measured. We're just going to look at how we compare earthquake magnitudes. So it's that amount of energy released is determined from the logarithm of the amplitude of waves recorded by seismographs. Way beyond the scope of this course, but the differences in intensity levels, what that actually means, like what it means to be 7.8 on the Richter scale compared to 8.9 on the Richter scale is what we're looking at. So the Richter scale is logarithmic. So a difference in 1 unit in magnitude corresponds to a factor of 10 difference in intensity. So the difference between 8 and 9 would be a factor of 10, right? So that would be times 10. Difference between let's say 7 and 9 would be times 10 times 10, right? Or 100. So each whole number step represents a 10-fold increase in intensity. So magnitude 9 earthquake is 10 times larger than a magnitude 8 earthquake, 100 times larger than magnitude 7, and 1,000 times larger than a magnitude 6 earthquake. A magnitude of 1 on the Richter scale is equivalent to a large blast at a construction site using about 14 kilograms of TNT, which is not that much. And it's 10 times as intense as the zero reference point, which would be like no release of energy. So an earthquake with a magnitude of 2 is 10 times 2 or 100 times as intense as that zero reference point. Any earthquakes having magnitudes in excess of 6 on the Richter scale are considered dangerous. The largest yet recorded, the Chilean earthquake of 1960s, that was right up here at the top at 9.5, that's pretty high. It registered 9.5 on the Richter scale. The most powerful one recorded in North America was an Alaska quake in 1964, which was 8.4 on the Richter scale. We don't usually, Alberta is not a place where we would feel earthquakes, but I've definitely felt them when I lived in Victoria, and that surprised me. And Ontario and some places in Manitoba can feel earthquakes as well. So just practicing a little bit with this, the powers of 10. So if there's basically a difference of 1 between the magnitudes, then that corresponds to a 10 to the 1 times of intensity, so an intensity of 10 times. So magnitude 8 is 10 times as intense as magnitude 7. If you have a magnitude 7 earthquake, we want to know how many times as intense is that as an earthquake of magnitude 3. So there's four steps, like 3, 4, 5, 6, 7, between 7 and 3. So it would be 10 to the 4 or 10,000 times as intense. An earthquake of magnitude 4 is how many times as intense as an earthquake of magnitude 6. Okay, now so there is a difference of 2 between here, but we want to look at 4. And if we go 4 to 6, there's actually a negative 2, so 10 to the negative 2, right? Because you're going up instead of down, whereas in all these other ones you're going down. So that means it's 0.01 times as intense as an earthquake of magnitude 6. Okay. An earthquake of magnitude 4.8 is the same thing. If we go 4.8 and 6.8, that's again a difference of negative 2. So it's 0.01 times as intense as an earthquake of magnitude 6.8. The 1960 earthquake in Chile, which was 9.5 on the Richter scale. 1976 earthquake in Italy, so that was 6.5. So that is 10 to the 3, or 1,000 times as intense. And the earthquake in Colombia in 1983 is 5.5. So the 1960 earthquake in Chile, which is 9.5, is 1,000 times as intense as the 1976 earthquake in Italy, which is 6.5, and it's going to be 10 to the 4, or 10,000 times as intense as the 1983 earthquake in Colombia. The 1966 earthquake in Turkey was, so that 66 earthquake in Turkey is 6.9, and the 1933 earthquake in Japan is 8.9. So again, that's a difference of negative 2. So 10 to the power of negative 2, or 0.01 times as intense. Now, unfortunately, the kinds of questions that you're going to get based on the Richter scale are not always going to be quite this simplistic, because the differences are not always a whole number. If we look at this, if we look at 5.5, we want to compare 5.5 to 6.3 or to 6.9. We can't do that using the method we use, because it's not a whole number of steps. So we have to have some method for comparing those types of earthquakes. So how would we compare the intensity of the 1960 earthquake in Chile, which is magnitude 9.5, and the 2005 earthquake in Chile, which was 7.8? So compare the intensities of magnitude M1 and M2, we're going to consider the following. And I know that on your sheet that I've printed out, the formulas are here, but again, my smartboard doesn't like bringing up the formulas, so I'm just going to fill in what we're missing here. So this is M is equal to log of I divided by I naught, okay, where I is the earthquake intensity and IO is some reference intensity. So we can say that the magnitude of earthquake 1, which will be Chile, right, this will be magnitude 1, sorry, this one over here will be magnitude 1, that 9.5, it's equal to log of the intensity of earthquake 1 divided by a reference intensity, and the magnitude of earthquake 2 is log of the intensity of earthquake 2 divided by a reference intensity. Okay. So then we can use, if we want to compare these, right, we want to find the difference between the two. So we want to find the difference in magnitudes. We want to go M1 minus M2. So M1 minus M2 is going to be equal to log I1 over I2. And we're going to show how we got that. Okay, so that's what we're trying to do, is to get to that. So we have M1 minus M2 is equal to log of I1 over IO minus log I2 over IO. We can split this up here because we have division. So we're going to use our quotient law and write this as the first one is going to be log of I1 minus log of IO. And then that's minus the second log there, which is log of I2 minus IO. Now you don't need to be doing, you're not going to have to do what I'm doing here. I'm doing this so we can develop, or you can see where the formula that we're eventually going to use actually comes from. If we simplify this, we get log I1 minus log I0 minus log I2 plus, because we've got negative times a negative, so that's plus log I0. So then what happens is this negative log I0 plus log I0, they cancel, and we're left with log I1 minus log I2, which can be simplified to log I1 divided by I2. Okay, so that's our difference in intensities. What we want to do here now, though, is we want to convert this to exponential form, because that is what we actually want to find here. So if we convert this to exponential form, remember this is log base 10, so we're going to have 10 to the power of M1 minus M2 is equal to the intensity of 1 compared to the intensity of 2. And then that's the formula that we're using here. And this is not on your formula sheet. You'll usually not be given it. You have to figure out how to get that. Usually what you'll be given in a question is just this, that relationship there, which can help you. I mean, you have basically what you need there. It's just that if you converted this to exponential form, this would be 10 to the m is equal to I over IO, right? What you want is M1 minus M2 over I1 over I2. That's the only change that you need to make there. Okay, so this is probably worth memorizing, even though on the diploma maybe you'll get one question on it. So we'll just do a couple examples here using that particular formula. So we want to know how many times more intense was the 1960 earthquake in Chile, which is magnitude 9.5, so that's M1, than the 2005 earthquake in Chile, which was magnitude 7.8, so that's M2. So we have that this is just, this I1 minus I2, that just says intensity of I1 compared to I2. And that equals 10 to the power of 9.5 minus 7.8. And we would simply put that into our calculator, remembering to use brackets when you find, when you put in your exponent. So we would do 10 to the power of, let's see, 9.5 minus 7.8. Which is 1.7. And so then 10 to the power of 1.7 gives you 50.1, or approximately 50 times as intense. Okay, and that's nothing we could have gotten with our, with the way that we were doing it on the first page. Okay. Now, you can also be given a question where you have to solve for the exponent. So we have a major earthquake of magnitude 7.5. So this, we'll say this is M1, and it's 375 times as intense as a minor earthquake. So that 375, that's our I1 divided by I2 is 375. Okay, and a major earthquake, minor earthquake. So is the magnitude of the minor earthquake greater or smaller than 7.5? Well, use your major and minor to figure that out. So it's going to be smaller. And then we want to determine to one decimal place the magnitude of the minor earthquake. So we have I1 divided by I2 is equal to 10 to the power of M1 minus M2. So 375 is equal to 10 to the power of 7.5 minus M2. And this is not too hard to solve. We are going to convert it to log form. We don't even have to mess around with our change of base law because this is base 10. So we have log base 10 of 375 is equal to 7.5 minus M2. So just figure out what log 375 is, or you can do some rearranging here. We're going to have M2 is equal to 7.5 minus log 375. And that equals 4.9. So that is the magnitude of earthquake 2 on the Richter scale. Okay, so that's the Richter scale. We're going to look at loudness of sound and pH, which is essentially the same thing. All that we're really changing in our formula is what the variables stand for. So if we go to loudness of sound, what we're working with here is decibels. So the loudness of sound was originally measured in bells, and that's named after Alexander Graham Bell. But the current unit we use now is a decibel, which is 1/10 of a bell. So, 10 decibels equals 1 bell. Like that. Okay, so the Bell scale, like the Richter scale, is logarithmic. A difference of 1 bell or 10 decibels corresponds to a factor of 10 difference in intensity. So, like if we had, from 50 to 100, that's would be a difference of 10 to the 5 in intensity, or 100,000. So a leaf rustling, which is 10 decibels, is 10 times as intense as the threshold of hearing, which is 0, which is is just when you can start to hear. A whisper, which is 30 decibels, or 3 bells, is 10 to the 3, or 1,000 times as intense as the threshold of hearing, or 10 to the 2, or 100 times as intense as a leaf rustling. So we'll just look at some simplistic comparisons here, like we did with the earthquakes. So we have a power saw, which is 120 decibels, is how many times as intense as a telephone dial tone. So there are, if you go 120 minus 80, you get 40. Divide that by 10, which gives you 4. So that's 10 to the 4 times as intense, or 10,000. A jet engine at 20 meters, which is 145 decibels, is how many times as intense as the threshold of pain, which is 125. So 145 minus 125 is 20, divided by 10 is 2, so that's 10 to the 2, or 100 times as intense. And a whisper, which is 30 decibels, is how many times as intense as a conversation. So 30 minus 60 is negative 30, divided by 10, which is negative 3, so 10 to the negative 3, which is 0.001. But again, we can only compare differences, like of when there's like a difference of exactly 10 or multiples of 10. So we need a way of comparing sound when the differences are so we could compare, say, a leaf rustling with something that's maybe so 65 with piano playing. So we want to be able to compare differences in levels of sound when we don't have nice clean multiples of 10. And so we end up using a very similar formula to the earthquake one, because what we start with is that decibels is equal to 10 times log of whatever intensity versus the intensity at the threshold of hearing, which is 0. So we can convert this to something that compares intensity. So this is intensity of 1 compared to 2. And that's equal to 10 to the power of the loudness of sound in decibels of sound 1 and the loudness in decibels of sound 2. But we have to divide that by 10. Okay, so that's the difference. It's the same formula as the earthquake intensity, but because decibels is 10 times bells, we have to have that dividing by 10 there. And again, you'll probably want to memorize this. So, how many times more intense is the sound of a piano playing, which is 67 decibels, so we'll call that dB1, than a whisper, which is 22 decibels, so dB2. So we have I1 over I2 is equal to 10 to the power of 67 minus 22 over 10, which is 10 to the power of 45 over 10, or 10 to the power of 4.5. Okay, and that gives us 31,622.77, or 31,623 times. And again, we might have to solve for the exponent. So given that decibels equals 10 times log I divided by I0, show that the decibel level for the threshold of pain, so this will be dB1, has a sound intensity of 10 to the 12.5 times I0. Okay, so what we're looking at here then is we have, this is our decibels, so we're starting with this formula. Decibels equals 10 times log I over I0. So 125 is equal to 10 times log I over I0. So we have 12.5 equals log I over I0. We're going to convert this to exponential form. So 10 to the power of 12.5 is equal to I1 over I0, or sorry, not just I, so the intensity is equal to I0 times 10 to the 12.5, which is the same thing as that, I've just written it a little differently. I guess we didn't solve the exponent there, that's okay. Okay, and the next thing we want to look at is pH. So if you've taken chemistry, you'll have a little bit of familiarity with pH. And we're going to do two things with it. We're going to look at comparing acidity and alkalinity, and then we're also going to look at the formula that we actually use to solve for pH when we know the hydrogen ion concentration, and then solving for the hydrogen ion concentration when we know the pH. So the pH scale has been around since about 1909. It was invented by a Dutch chemist named Søren Sørensen. And it represents the expression pH stands for power of hydrogen, because it measures an extremely wide range of hydrogen ion concentration in substances, from very, very acidic substances to very, very alkaline substances. So it measures the range of hydrogen ion concentration by determining the acidity or alkalinity of a solution. pH values below 7, so this way here, as it says here, is acidity, increasing acidity, and this way is increasing alkalinity. So it's kind of a weird scale, because sort of what's neutral is in the middle, and then it goes up or down from there. It's similar to the Richter scale. The pH scale is logarithmic, so difference in 1 unit of pH corresponds to a factor of 10 difference in intensity. So 6 is 10 times as acidic as 7, 5 is 100 times acidic as 7, 4 is 1,000 times as acidic, and so on, and you can also do it the other way. So if vinegar has a pH of 3, then it's 10 times as acidic as tomato juice, which is 4, and 100 times as acidic as normal rain, which is pH of 5. On the other hand, household ammonia, which has a pH of 11.5, is 10 times as alkaline as milk of magnesia, which is 10.5, and 1,000 times as alkaline as seawater, which is 8.5. So we've got this little table here with a few solutions. This starts with acids at the top, and then will be alkalines at the bottom, and then there's your neutral, so that is increasing acidity and increasing alkalinity. So tomato juice, if we want to find tomato juice and compare it to pure water, there's a difference there of this is 4 and 7, so it's 10 to the 3 or 1,000 times as acidic as pure water. Eggs, which is 8, and pure water, so that's 8 and 7. And now this is where when we're going this way, up here this way, we're going to subtract the normal way, but we're going this way, we have to sort of do it backwards. So 8 is 1 bigger than pure water, so it's 10 times as alkaline because we're looking at the alkalinity as opposed to acidity. But eggs are, if we look at compare eggs to pure water, so eggs, so then we would subtract the normal way, so this being 8 and this being 7, we would go 7 minus 8, which is -1, so it's 10 to the -1, or 0.1 times as acidic as pure water. Milk of magnesia, okay, is 10 times as, we want to know alkaline or acidic. So blood is 7.5, and we're going up the scale there, so as alkaline. And what we want to know, what is 100 times as acidic as normal rain? So there's normal rain at 5, so that's going to be, I'll put vinegar, 100 times, yeah, so we want 2 up, that's right, so vinegar. Eggs are 1 over 10,000 times as alkaline as, so eggs, so that would be washing soda. If you have the decimal, that means it's less alkaline, right, as opposed to more alkaline. Okay. So then we can compare acidity the same way we could compare decibel level and as well as Richter scale. So we just use 10 to the power of pH 1 minus pH 2 will tell us the difference in intensity. So pure water has a pH of 7, swimming pool water is 7.5, and seawater is 8.4. So seawater is how many times as alkaline as pure water? Okay, so seawater versus, and we want alkaline, so we're going to go 10 to the power of 8.4 minus 7, which is 10 to the power of 1.4, which is 25 times as acidic. Seawater is how many times as alkaline as swimming pool water, so same thing, 10, so seawater versus swimming pool water, so it's going to be 8.4 minus 7.5, or 10 to the 0.9, which is about 8 times. The other thing we can do with pH is to use the pH formula. So pH is equal to negative log of the hydrogen ion concentration. So this is not on your formula sheet. And that negative log, so that just goes in, you just push negative log and then put in whatever the hydrogen ion concentration, which is expressed in moles per liter. Every question I've ever seen on the diploma or on practice questions involving pH will give you this formula. Okay? But the thing that was really annoying, and I shouldn't talk about this because I'm not really supposed to talk about diplomas, but they had something with a negative pH on the last diploma exam, which I thought was very odd. It's a very rare thing, so just don't get freaked out if you end up with a negative pH. Just use the formula the same way. So patient gave a urine sample which is found to have a pH of 5.7. We want to know what is the hydrogen ion concentration. So we have 5.7 is equal to negative log of the hydrogen ion concentration. Okay. We want to solve for the argument, which means we need to convert this to an exponential form. So we're going to move that negative on to the other side. So negative 5.7 is equal to log, remember this is base 10 of H. So we're just going to have 10 to the negative 5.7 is equal to the hydrogen ion concentration. And if we put in 10 to the power of negative 7 in our calculator, we get 1.99 times 10 to the negative 6, which to 1 decimal place would be 2.0 times 10 to the negative 6 moles per liter. And then, of course, we can use the formula the other way, which is a little bit simpler, where we have the hydrogen ion concentration, so that's our H+, and we want pH. So pH is equal to negative log of 3.4 times 10 to the 4, negative 4 moles per liter. And we would just put that in our calculator. And remember, you should get a number somewhere between 0 and 14. And when you calculate this, you get 3.5. Okay, and that's it. That's all of our, the whole unit on exponential and logarithmic functions. Your homework is the worksheet, again, which is questions 1 to 13. There's also your unit assignment, which you can work on, but you will get all day tomorrow, or all of tomorrow's class, to finish that unit assignment, because it will be due at the end of class. So have a good day, guys.